Algebra 2 Cram, New York State, Algebra 2 Regents, Common Core, Basics, Trigonometric Functions, Concept number 20, Cosecant of 30, 45, and 60 degrees. The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. What we're doing here is effective. I'm coaching you to turn your wants and desires of getting an A or perfect test scores into a brand new paradigm. I want to include everyone who needs a boost in Algebra 2, and if I could stick every single math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I probably would. So inbox me at memedicine@gmail.com to get your healthy dose of this complete Algebra 2 cram session beyond the trigonometry series. You have lots of pairs, classmates, and colleagues who could also use a boost as well, so tell them to inbox me at memedicine@gmail.com so that they too can order the complete cram session. And you'll be glad you spread the word because they'll make great study buddies. And last but not least, the concept of cramming often has a negative connotation. But what people are actually thinking of is hurrying, which is a result of fear and can consequently be destructive to your overall learning process. We're not hurrying here, we're cramming, and there's a huge difference. Hurrying is jam-packing tons and tons of unorganized information into your mental DNA over tiny amounts of elapsed time, whereas cramming is taking quantum leaps in your understanding in an organized way in what seems like an instant. Let's delve into the concept of the cosecant of these angle values. All right? Cosecant of 30 degrees, 45 degrees, and 60 degrees. What are the exact values of the cosecant of theta when theta is equivalent to 30 degrees, 45 degrees, and 60 degrees? Definitely press pause if you need to, and I'll give you a moment to think. All right, so hopefully by now you are able to arrive at an answer, and if you didn't, that's completely fine. We're going to work through this together. Before expressing the exact values of the cosecant of 30 degrees, 45 degrees, not 40, and 60 degrees, we need to understand the concept of standard position, okay? And doing this is going to simplify finding any trigonometric value, regardless of the cosecant, secant, or cotangent cofunctions, as well as sine, cosine, and tangent, okay? And because the angle values 30 degrees, 45 degrees, and 60 degrees are acute angles, acute meaning they fall between the quadrantal angles 0 degrees and 90 degrees, they're acute angles in standard position in quadrant 1. So this means that they're going to have 7 key features that we're going to discuss now, which will simplify finding any trigonometric value. The first key feature is that the vertex for such angles is located at the origin. The origin has the x-coordinate 0 and the y-coordinate 0, so this location is 0, 0. Okay? The ray on the positive x-axis, which is slightly bolded in this region, is called the initial side ray. The other ray terminates in quadrant 1 after these acute angles grow in the counterclockwise direction, and this is called the terminal side ray, but we're going to call it R for short. So our third standard position feature is calling this terminal side ray R, okay? The fourth feature is that we're going to play around a little bit. We're going to cut R off at this point, P, P being short for point, and point P has the coordinates X and Y, okay? All right, so a fifth feature is that for our purposes, we're going to resolve what's now a terminal side segment or a segment length into its x and y components, or coordinates rather. So this side, the terminal side array, is no longer a terminal side array, it's a segment, okay? And here goes our resolution of this segment. So the extent of this segment, which is bound between the vertex and point P, goes to x in the horizontal direction, and it rises to the level of y in the vertical y-axis direction. And notice here we're dealing with the coordinate points of P. And for any terminal side segment where you resolve it into its x and y components, what you then create is an imaginary triangle, a right triangle to be exact, okay? Where the coordinate points don't necessarily have to fall in quadrant 1. They can fall in quadrants 2, 3, and 4. But when that happens, that the sign of the coordinate points may change. So for instance, let's say the extent of the terminal side segment is in quadrant 1 or quadrant 4. This means that the x-coordinate is going to be positive. But let's say that the extent of the terminal side segment looks something like this or like that. This means that the x-coordinate is in the negative realm of the x-axis, so therefore the sign would be negative. And you could say the same thing for the y-coordinate. If the terminal side segment terminates in quadrants 1 and 2, the y-coordinate will be positive. But let's just say that it terminates in quadrant 3 or 4. We're now in the realm of the negative aspect of the y-axis, so the y-coordinates would be negative over here, okay? But we're strictly dealing with quadrant 1 because we're focused on our acute angles 30 degrees, 45 degrees, and 60 degrees. So we don't have to worry about all these other scenarios. And in our scenario, x and y are obviously going to be positive because we're in the positive realm of both the x and y axis, okay? All right, so the fifth feature, again, was that our height extended, or the sixth feature, rather, was that the height extended to the y-coordinate of P, which is y. These y's are the same. And the last feature regards the hypotenuse of this right triangle, or the segment length. The segment length is a measure of magnitude as opposed to being a coordinate position like x and y. So its value will always be positive, and that's because you use a variation of the distance formula to calculate r, or the hypotenuse length, okay? And so basically r is the result of the square root of the x-coordinate of p squared plus the y-coordinate of y squared, okay? But the caveat is that the initial point has to be at the location of the origin, because the distance formula says that the square root of the final x position minus the initial x position of a segment length, well, conveniently for our purposes, the initial position was at the vertex and has the location 0, 0. Therefore, we plug in a 0 here for the initial point of the x-coordinate, and we can imagine a y minus 0 for the initial point of the y-coordinates. But we don't have to be redundant and write 0. We can just exclude it to save on time and ink, okay? And that's why this is a variation of the distance formula. This was the seventh feature of this whole standard position concept, and it's just basically for you to note last that the measurement of the segment length is always positive. Okay, so now what I previously said about being able to use this imagined concept of standard position to find out any trig value. Well, in this case, we're dealing with the cosecant of some angle theta, theta having these specific values. Okay, and before finding the secant, we would have to basically, or you don't necessarily have to, but the secant is just the reciprocal identity of the trigonometric function, the sine of some specific angle theta, and that ratio is always going to be determined by the y-coordinate, or the side opposing the angle theta of interest, divided by the hypotenuse of this specific right triangle, okay? Therefore, if the cosecant of theta is the reciprocal identity of the sine of theta, all you're going to have to do is flip that fraction. And so the cosecant of theta now becomes the hypotenuse over the corresponding y-coordinate, okay? So just, review really briefly the sign of these common acute angles. We're just going to do a quick run through. These are values you should memorize. Sine of 30 is 1/2. The sine of 45 degrees is the square root of 2 over 2. And the sine of 60 degrees is the square root of 3 over 2. Okay? Now for the reciprocal identity, here things get a little interesting. Obviously, if you flip this fraction, that means that the cosecant of 30 degrees would be 2. The cosecant of 45 degrees is going to be 2, but this might not be so obvious. When you flip this fraction, you're going to get 2 over radical 2. But in the world of math, radical 2 is an irrational number, meaning that when you try to take the square root of 2, it's going to create a never terminating decimal. And in the math world, that can't be in the denominator. So because this is an irrational number, what you have to do is rationalize the denominator. So let me show you what I'm talking about. This would be the original cosecant of 45 degrees, okay? But this is bad. We don't want that rational 2 in the denominator. So what we therefore have to do is basically rationalize the denominator, and we just do that by multiplying by the irrational expression in the numerator and the denominator. So when you square an irrational number, what you're going to get is the number inside the parentheses, okay? And this then becomes 2, radical 2, and a radical 2 squared in the denominator, or radical 2 times itself, would yield 2. Well, notice these two cancel, the 2's cancel, and that's how we get our radical 2 for the cosecant of 45 degrees when theta is 45 degrees, okay? All right, we have a similar situation with the cosecant of 60 degrees. The final solution will be 2 radical 3 over 3. And again, let me just do a quick run through of how this comes into being. When you flip this fraction, because the cosecant of 60 degrees is the reciprocal identity of the sine of 60 degrees, you're going to get this. You're going to get 2 over the square root of 3, but we don't want an irrational 3, square root of 3 in the denominator. I think 3 is irrational, whatever, we just don't want undefined square roots in the denominator. And so what you're going to do is rationalize the denominator by multiplying by the irrational radical in the numerator and the denominator. Well, this is then going to become 2 radical 3, and radical 3 times radical 3 is the same as squaring it. So when you square a radical, you're just getting rid of the square root sign, and that's going to leave you with 3, okay? So that's how we got this answer here. All right, so that's about it. Thanks for sticking with me till the end. And what I want you to realize is that intellectual comprehension of this material was not difficult at all. And after the short amount of time it takes to complete the entire cram session, when you order, you'll be able to answer a battery of questions about any Algebra 2 concept. Good luck studying, and thanks for tuning in.